Okay, in this lecture we're going to talk about spray diagnostics, and it's kind of funny because in the last lecture we talked about how to use particle scattering in a useful way, and mostly in this case we're going to try to talk about how to avoid the corruption caused by particle scattering. So I'm going to talk a little bit about the spray problem in this issue of optical depth and scattering in sprays. Then I'm going to talk about time-gated imaging, ballistic imaging, and optical sectioning. Up until now, I don't think I've ever shown you any. I've shown you a few things that have come from my lab, but not very many. Just because I had the pictures, so I used them. But I haven't shown. Mostly, I've been talking about what other people do. These are things that my group does. A guy who was a postdoc of mine started this while he was my postdoc, but now he does this on his own as his own thing, and so this is closer to the kinds of things that I do. So how to take pictures in a spray. So what's the spray problem anyway? I mean, if you think about it, we use liquid fuels because liquid fuels have very high energy density, but as we all know, a combustion reaction occurs between things in the gas phase typically. Coal is an exception. You can get oxygen diffusing into pores of coal and reacting on the surface, but that's the exception. So you need to be able to convert this liquid into a vapor phase, and you do that with a spray. And this is what the regions of a spray people typically talk about. And I'm going through this because I'm guessing most of you don't study sprays. It's a niche thing in the combustion world. You have this liquid flow, and it comes out and has to break up. So this thing is called a liquid core, this stuff that remains. This is called the spray formation region because if you look up the dictionary definition of a spray, it's a collection of small droplets moving through a gas phase. So you're producing the spray here. So the point is that down here, we've already actually talked about some of this. Down here in the what they call the dilute region, or downstream in the spray, you can use lots of different techniques. You can use imaging, like planar laser-induced fluorescence, me scattering, or this technique, Slippy, I'll talk about, and phase Doppler at single point. The thing is that you run into serious problems in this spray formation region because it's optically thick. And so that's when it was about 1994 when some spray people started to complain about we can't see these things. And I asked what's the problem, and they explained it, and I realized, oh, there's some techniques people use in the medical world that maybe you could use here for this problem. And it turns out it was true. It's also true that the flow inside the nozzle has a huge effect on the flow exiting and how the spray breaks up. So the spray breaks up. How does the liquid core break up? Well, it's by turbulent kinetic energy to begin with. If you think about it, it's wall-bounded turbulence when it's inside the nozzle, and it's immediately released with no wall. It has a whole lot of radial motion, radial kinetic energy. And if it has enough kinetic energy to overcome surface tension, it will break off a ligament or a drop or something like that. It's helped quite a bit by shear with the gas on the outside, especially in an engine where the gas is very dense. So shear helps that out a lot. It can also cavitate inside the flow, and that will totally change the way the spray breaks up. Another thing that's interesting is inside a diesel injector, for example, there's a needle, and as the needle pulls up, this is not an axisymmetric system, especially because the liquid's going to go out sideways. And it turns out that you can set up a large amount of vorticity inside what's called the sac region of the injector, and the rotation of that fluid actually survives to the exit. We've actually measured a little bit of rotation, and any kind of rotating flow like that is going to have some centrifugal force acting on it that's going to cause it to spread. So all these things can contribute to spray breakup. So if you look inside the nozzle, you can use a technique called X-ray phase contrast imaging or optically transmissive tips. That's what we work on, optically transmissive tips. And you can see in this case, there's a sac volume. This is the edge of the spray, the injector, I'm sorry. This is the edge of the injector. This particular thing was made out of acrylic, which is index matched to the fluid mostly. Here's the sac volume. Here's the hole. There's a little bit of string cavitation coming out and growing until we come out. So this is out in the gas. Okay, so you're seeing a little bit of cavitation happening. This is the spray formation region, and this is where you see that dense droplet cloud. And the trouble is, it's almost like a really intense storm cloud that comes overhead. It gets really dark, right? It's all because of scattering off axis, sending the light sideways. So there are several ways you can make measurements inside that region now. You can use a technique called X-ray radiography, which is an absorption-based technique. And it measures the absolute mass in the liquid. The thing about that is that it's an average technique, so you do it over many pulses at a single point. So it takes forever to map out the mass distribution, but that is a way to get a good picture of what really is the mass distribution in the near field of a diesel spray. Or you can also do some X-ray fluorescence tricks. Until recently, it's been impossible to look inside this droplet cloud and see what the structures look like. What does the intact liquid core look like? That's the point, and people couldn't see it. And that's because of the dense droplet cloud. And so this technique called ballistic imaging and optical sectioning in a different way can see into that region. And it does that by minimizing corruption caused by scattering off axis by the drops. This technique, Slippy, can see into a spray that's not quite as dense as this picture. So Slippy can go up to an optical depth of, say, 6. Ballistic imaging can see to an optical depth of about 12 or 13. As a reference point, human tissue, 1 millimeter thick of human tissue has an optical depth of 11. That's not actually a fair comparison, though, because the scatterers in human tissue are much smaller. Remember we were talking about the spatial distribution of scattering? The scatterers are much smaller, which means that they scatter much more in all directions. Fuel droplets are big. They scatter in a very strong forward lobe. So there's actually a difference between the two. So optical depth. We talked about it in Lecture 2 in terms of Beer's law. So we said the transmissivity is IL over I0 e to the minus optical depth, where we're defining it here. This is the same expression we used before. The number of events. When we talked about Beer's law before, this was an absorption cross-section. This is now an extinction cross-section times L, where in this case, extinction is by absorption and scattering. Okay, mostly it's scattering in a spray. And L is the path length across the spray. So when I say optical depth of 6 or optical depth of 12, that's what I'm talking about. Trying to measure optical depth in a spray is really messy. In fact, I wouldn't even try it. The measurement depends on the drop size distribution, right? Here's a small drop. There's a big drop. This one's going to send a whole lot more light forward. So if you have a spray here and you send a laser beam through and you try to collect it there, the amount of transmitted light you measure depends on the drop size distribution, not just how many drops are there. It also depends on the angle, the collection angle of the system. So it's actually not easy to measure optical depth in a spray. So based on Monte Carlo modeling we've done, we showed that in the normal spray, in the normal region where you get the drop sizes that you'd find in a normal spray, the OD is very close to the number of interactions or the scattering order. So if the laser beam's coming through your spray and it hits 10 drops, we call that an optical depth of 10 because the Monte Carlo code, which sends photons through the spray, says that's about what happens. So what do we mean by single scattering regime? So here's my cartoon of a collection of drops. Here comes light. Okay, here's an unscattered light. That's a ballistic photon, it's called. That's why this name is called ballistic imaging. Here's a single scattering event, sends a photon off in that direction. Okay, that single scattering regime. This one scattering event can be modeled by the Me formalism I talked about in the first lecture. In the intermediate scattering regime, which applies to dense sprays, you see more than that happening. Okay, here's an order 2 scattering. Okay, here again you get some unscattered or ballistic photons coming through, and in general, this is for scattering events on the order of 2 up to 9. Then the optical depth is about 2 up to 9. To calculate what happens here, you have to use a Monte Carlo code, and we have one. And we launch billions of photons through this thing so we can analyze how does this actually behave, what really happens when light goes through a spray. Then finally there's this thing called a multiple scattering regime where you get even more than 9 scattering events. And in that case, the relative contribution from the different scattering orders is the same. And so you can use this thing called the diffusion approximation, which kind of assumes everything is uniform. But we're not really in that regime. Some of what we do is in that regime, but a lot of what we do is in the other regime. So you can't use the diffusion approximation. So we use Monte Carlo simulations. So let me show you some results. This guy who was a postdoc with me, Edward Baracal, he's now at the University of Lund. He's the one who developed Slippy. He also wrote this Monte Carlo code. So the code can actually calculate all kinds of things like what's the distribution of light scattered to the side, what's the distribution scattered forward, and so forth. I'm only going to talk about the amount of light that's scattered forward. What's really nice about this code is we can see things with it that you can't see with an experiment. We can see which scattering orders are coming out of the spray when, and so on. So what happens when you try to, this is my cartoon of a spray, for example. So we're going to send light through the spray. Most of it's going to scatter all over the place. Well, what happens for what comes out? So we're going to look at what we do experiments where we put polystyrene spheres inside a cell, and we choose the polystyrene spheres so they have the same scattering phase function. You remember those pictures I showed you with the different lobes and everything? That's the scattering phase function. We choose them so they have the same scattering phase function as a diesel droplet of the range of sizes that you'd see in a spray. So we're going to get the same kind of scattering behavior, but this thing sits still and it doesn't make a fuel mess all over your table. So we can also predict what comes out. And so this is an acceptance angle for the optics. What kind of optics will you set up here? And it'll have these acceptance angles. So we can change the droplet size here, which changes the scattering phase function. We can change the optical depth. We can do that experimentally, but we can also do it in the Monte Carlo code, and we can look at different acceptance angles. So here are some results. This is for a small scatterer, okay? And this is light in the forward direction. It goes through a cell that's 10 millimeters thick. It's a monodispersed collection of scatterers, so they all have the same size, with this scattering size parameter of 3.6, so it's a small scatterer. Here's the scattering phase function for that, and you can see it's not very much different from Rayleigh scattering. It is different, but not that much different. And so what we're looking at here is an optical depth of 5, 10, and 15. This is for an acceptance angle of 11.4, that's the half angle, and here's for a smaller acceptance angle, 5.7. And these colors are for the different scattering orders, okay? So the gray, there's a gray right there. That's ballistic photons. That means they came through without hitting any drops. That happens. Light comes through without hitting any drops. So then the red is the first order, second order, third, and so forth, okay? And the black is the sum of all the contributions. Now you're going to look at this and go, wait, all those colors don't add up to that. That's because we did not include all of the scattering orders because it would just be a big blob and you can't see what's happening. So you look here at a fairly low optical depth and you see that there's this pulse that comes out in the leading edge. Those are mostly ballistic photons, but a little bit of first order photons as well. And then there's a little bit of stuff that's scattered around coming out later in time. If we close down the angle, if you think about it, the light that's multiply scattered, most of it is scattered off axis. So if we close down the angle, we'll capture less of it. We'll capture less of the stuff that's multiply scattered. And that happens. Now if we go to high optical depth, you can see there's still a little bit of what looks like ballistic light. It's really ballistic and first order scattered light. And then there's all this garbage from stuff that's scattered off axis. We close down the angle, and this, notice that we just changed the order of magnitude of the intensity of light coming out here, okay? So much less light comes out, but we see the spike from the leading edge, and then you get the garbage. And when you go to optical depth 15, just forget it. So this is actually somewhat close to what human tissue does, and so ballistic imaging, this technique I'll describe to you, was meant to look through human tissue. And the problem is that if you get a lot of light scattered almost like in a Rayleigh pattern, and so it goes off and bounces all over the place and it gets really highly corrupted. So when it comes out, there's a huge amount of corrupted light that doesn't tell you very much about what was inside because of all the scattering. Now if we look at bigger scatterers, so this is X is 17.9. That's reaching fuel drop size. Okay? That has a huge forward lobe. All fuel drops have got huge forward scattering lobes. And what's interesting about the forward scattering lobe is it has the same direction as ballistic photons. It also has the same polarization as ballistic photons. And it comes out almost at exactly the same time as the ballistic photons. So let's look at optical depth 5, the big angle and the small angle. They don't look much different. That's because this thing is actually feeding light straight in that direction. We go to optical depth 10. You see as you close down the angle, it kills off more. But you see there's a strong leading edge that looks almost ballistic. Optical depth 15. You're not seeing these other orders, but there is light getting through that's scattered in the forward direction. So let's talk about ballistic imaging now that we understand a little bit more about light scattering through sprays. So this is, I've shown you this before. It's my cartoon of a spray. This would be the liquid core. There's the droplets. Here's light coming in, right? And the light is getting scattered off axis. So what I'm trying to do is take a shadowgram image of the liquid core. I want to see the liquid core and I want a shadowgram image of it, but the droplets are corrupting everything. They're just masking everything because they're scattering things off axis so much. Okay? So that's what I want. It turns out there is some useful imaging light that comes out. Here I'm going to be a little bit artificial again. I'm going to draw a distinction between light that's scattered and light that's refracted. So scattered light, multiply scattered light off axis is what corrupts the image. What I want is a shadowgram. That's based on light that's refracted by the big fluid structure, the liquid core. I want light that was refracted. I don't want scattered off axis light. And so useful imaging light has been refracted and not corrupted. The reason that this light is so highly corrupted, actually most of the light is blocked, and a camera's got only so much dynamic range. So much light comes around the spray that picture the D-slide showed you looked black. But if we somehow blocked off the light coming around the spray and tried to look through the center, we'd still see very little. And it's because if we can capture photons, this particular photon looks like it came from there. We're trying to map an object plane to an image plane. But what object plane are you going to have? There's one, every one of them's got their own object plane, which is why you can't create an image from that. These, however, do have an object plane. So we're going to try to capture the refracted light. So we're going to end up rejecting most of the light that comes around the spray and just capture a small population of photons. Even in a turbid medium like this, as I've alluded to, there are some photons that come straight through, and they're called ballistic. They actually make it all the way through without scattering. Okay? And then these, what I call quasi-ballistic photons, are the ones that are in the forward lobe. They have actually scattered several times, but because they're in the forward lobe, they look almost ballistic. You can see the first thing about them is they tend to come on the same center line as the input laser beam. They have a spatial signature, and in fact, if you use some kind of spatial filtering, you can get rid of the corrupted light. Now, if you send a short pulse through the spray, if you think about it, the ballistic photons travel the shortest path, so they'll come through first. Then come the quasi-ballistic, and then comes the corrupted light. And this is the Monte Carlo image, right? Which means we have already done spatial filtering. We've already killed off most of the stuff that's scattered off axis. But you see, we still do see light that's corrupted back here compared to the early light. So we can use these useful photons to see the liquid core if we can get rid of the corruption by the corrupted light. And you do that by looking for the signatures of the useful light. It has a directional orientation. It's on the center line of the input beam. The polarization is the same as the input beam, and it's first to exit. The ballistic photons themselves are also coherent with the input beam, so you could use interference or something like that to separate those out. But as the Monte Carlo code shows, you've killed all the ballistic photons by the time you reach the stage of a spray that you want to look at. So the dense region of a spray doesn't really have ballistic photons on offer. Especially, and if you think of it in terms of the tissue imaging, they would focus down and then average and then raster scan, because you can make tissues sit still. But you need to capture a full two-dimensional spray image in a very short period of time because they're transient. So you can't do it the way the medical people do. Why do these pictures look so crappy? I don't know. Anyway, this is a typical ballistic imaging system. This is a femtosecond Ti-sapphire laser. It's what's called mode locked. We'll talk about what mode locking means when we talk about lasers. This is an amplifier, so you send the pulses from the mode locked laser into the amplifier. And so it's running at 1 kilohertz. So the pulses that come out are about 100 femtoseconds long in time. A femto is 10 to the minus 15th, in case you forgot. They're at around 800 nanometers wavelength, so in the very near infrared. They have a pulse energy on the order of 4 millijoules per pulse. It turns out that 4 millijoules per pulse in a 100 femtosecond pulse means you have terawatts at the peak of the pulse. And in fact, if you actually focus this beam down in the laboratory, it causes a huge breakdown spark, just huge, it's like this big. And in fact, the guy from spectrophysics, when he adjusts it, when he comes in there, he focuses a little bit and he listens to the noise and makes the noise the loudest. And then you've got the most energy and the shortest pulse. So you take this beam and you split it into 2 beams using a filter. And one of these beams has to go through an adjustable time delay because we have very short pulses that have to land at the same place at the same time. Then we go through a polarizer because we're going to use polarization switching. So we want to have very clean polarization. And then we rotate the polarization 45 degrees. And we've already talked about how do you manipulate polarization with a crystal. So now we have linear polarization at 45 degrees. And we go through some optics to set the beam size in the object you're looking for. And then we go into this system here. So that's what the imaging beam does. The other beam is called a switching beam. And I think it's best to just pretend we move the beam block up here for now and get rid of the switching beam and talk about this business over here. This is called an optical Kerr effect time gate. It's like a really fast shutter in front of the camera. And the first thing in the time gate is a polarizer. And you set that polarizer so it will pass the polarization that you set here. So the beam comes through and it gets through that polarizer. Then you focus that down into a cell that's filled with a thing. Well, you can actually use a lot of different materials for this, but we use carbon disulfide. So at this point, the carbon disulfide is just this amorphous liquid. So the cell that's filled with carbon disulfide is almost like just a block of glass. It's completely passive. You change the size of the beam a little bit because of the index difference, and that's it. It's just like a block of glass. Then you up-collimate with this lens, and you go into this polarizer, and this polarizer is oriented to block that polarization. And these things get polarization rejection on the order of 10 to the 5th. So it really does shut off the light. So the shutter in front of the camera is off at this point. Now when you send this switching pulse through, this is a very, very short pulse. And again, there's a massive electric field in this pulse. Okay? And as it goes through the carbon disulfide, it actually orients the dipoles in the carbon disulfide. And it makes the carbon disulfide birefringent. So you design this Kerr gate so that it produces exactly the right amount of birefringence to rotate the polarization of this imaging beam to go through that polarizer. And the reason we use carbon disulfide is it will pass about 75% of the light through. Some of the other materials won't. So what happens is this pulse impulsively forces the CS2 cell to be birefringent, and then it's gone. And then the CS2 relaxes back to the state it used to have, and it has a sort of a natural diffusion time of about 1.5 picoseconds, which is 10 to the minus 12th. So this gate is open for only 1 to 1.5 picoseconds. So it's a very short time gate, and you control the time delay between the imaging and the switching pulses to select the part of the light coming through that you want. So if you think about it, this thing is doing some spatial filtering by controlling how much of the scattered light you collect. You have to be careful not to do too much spatial filtering because you'll kill spatial resolution if you do that. Then we're doing polarization filtering, and then we're doing time gating. So that's how ballistic imaging works. Here are some ballistic images of diesel sprays. This is the very first diesel spray ballistic image we ever took. This dark part is the liquid core. This out here, the light part, is where there used to be drops. This is the edge of the liquid core. And this is an interesting fluid structure. This was actually a thing called a Sturman diesel injector. It was going into 1 atmosphere of air. And you see these voids on the side. Those could potentially be caused by cavitation, for example. We don't know if this thing was cavitating or not, but I don't think it was hydroground inside, so it could have been cavitating. So that was when I was at the Colorado School of Mines. We took that data. I have colleagues at Coria in Rouen in France who also do ballistic imaging. Here are some of their results. This is during the steady period. This is after shutoff. And they wanted to show that they were actually looking inside the droplet cloud, so they took a shadowgram. And I often don't do that because it's a little bit unfair. The shadowgram is going to look all smeared because the camera's not fast enough. So, you know, you would have got a better looking shadowgram if you had used a fast shutter on the camera. But these cameras that we use are meant for very low light level imaging, and so they don't have fast shutters. The Kerr gate is our fast shutter. But anyway, you can see that this thing did sit inside that. Here's an effervescent spray, which is kind of an interesting thing. You bubble air into a liquid flow, so you make a bubbly flow here. And what's interesting about this, the argument is that the speed of sound in a two-phase mixture is much, much lower than the speed of sound in the liquid or the speed of sound in the gas, because there are all these interfaces it's interacting with. And because of that, this thing chokes at the exit in a situation where it wouldn't normally choke. And so what you see is a huge release of pressure as the liquid comes out. The bubbles burst, and they make this thing fall apart fast. So here's a ballistic image of this is a shadowgram. We went ahead and took a shadowgram. That's the ballistic image, or I'm sorry, the aerated spray, just a white light shadowgram. And here's a ballistic image of the same thing. And here you can see the really big drops I was talking about before. Those are in the geometric regime. This thing is actually seeing drops, but it's seeing the really big drops that refract light and are in the geometric regime. It's ignoring the small drops that scatter off axis. We did multi-pulse ballistic imaging. If you take 2 pulses in rapid succession, you get, here's a liquid-gas interface here. You can do image correlations, and I was talking to you before about how you have to be careful when you do image correlation. This is not PIV software. You can extract velocity vectors from 2 ballistic images. Here's 2 more ballistic images. We have a system at Chalmers in Sweden that will take 3 ballistic images. So this one is from the first 2 images. This is from the second 2 images. So you get 2 sets of velocity vectors, and from that you can get the acceleration of the liquid-gas interface. So this is the edge of a liquid jet in air, and these are acceleration vectors where we colored them based on their acceleration. So it goes from yellow to orange to red, from low to high acceleration, and the orange is about 5 meters per second squared. But these are also, if you think about it, the density of the air and the liquid are constant, so these are pictures of the forces that are acting on the liquid core. And I think this is kind of interesting. If you look right here, you see there's a ligament here, and there's a big force just blowing it out in that direction. I think that's a case where we accidentally captured a turbulent eddy that had enough kinetic energy in it to overcome surface tension and blow out the side of the wall. So what are the attributes of ballistic imaging? It's meant only for very dense sprays. It's a line of sight technique, which means you only see the edge, which is shown right there. That's the only use. It's just the edges of the 2 sides. And you get fairly good spatial resolution. It's not a drop sizing technique, although people see drops and think about it. We can go up to optical depths of 14. And you can extract statistics from the images. So that's what we use it for. Well, we had some sprays that were a little bit frustrating because ballistic imaging is a line of sight technique. So if you have a sequence of large liquid structures, maybe with air in between, and you send the ballistic imaging beam through this, it can't see those things. It'll only see these edges here. So we wondered, could you maybe find another way to look at those things? And so we did this technique called optical sectioning, where really all you do is turn ballistic imaging, or, you know, this used to be ballistic imaging with the beam coming through here. Now we moved it. We're going to scatter in that direction. Okay? They also do this in microscopy. That's called optical sectioning. So we're going to time gate backscattered light from inside the spray. You have to have a low light level detector now because backscattered light's not super strong. If you think about it, this time gate actually, if you think about the speed of light, the time gate actually represents a plane in space that's 450 microns thick. I didn't talk about it in the ballistic imaging, but that's actually happening in ballistic imaging as well. If I change the time delay between the gate and the image beam, I actually scan this plane in space. You can move it back and forth in space by changing the time delay. Which light are you accepting? Okay? And in fact, when you do ballistic imaging, if you're going to take a ballistic image, you have to adjust the camera lens to map the object plane to the image plane like you normally would in imaging. But then you also have to adjust the time delay, make sure that you're actually sampling from the same place the lens is supposed to be sampling from, and you're capturing the leading edge of the pulse. So in this case, if you think about it, this is a 1.5 picosecond time delay. That is kind of what it looks like. And there's the liquid core. So it dies off slowly, but you get this peak that you can scan back and forth if we're looking down on the liquid core, that is. So this is, we stuck a glass tube where the spray would normally be. And we scanned the time delay back and forth. So here's the signal as a function of distance. So we can convert the time delay that you set to distance. And so this peak right here is the front face of the glass rod. This peak is the inside face of the glass rod. And this peak is the other inside face of the glass rod. And in fact, these distances are correct for the size of the glass rod. Well, but the backscatter doesn't have that. I'm sorry. If you look at the scattering patterns, there's light scattered backwards, so why is it so weak? But if you look at those scattering patterns, those were logarithmic. And the forward lobe is what we use in ballistic imaging, and there's a very weak back end to those scattering phase functions, right? And that's what you're collecting now. That's the problem. And you're going to see what that does in a minute. It's actually, I'm not sure this is ever going to really work. We're still working on it. In fact, to be honest, I thought of this idea back in the year 2000 or something like that, and then people started to suggest to me we should do that, and I would say no. There will not be enough light coming through. We won't be able to see anything. And finally, my PhD student, Matthias Rahm is his name, he just defended his thesis. He just came in and insisted, and he said, I have an idea. We already have it set up in ballistic imaging. It's all set up. We can just backscatter. Give me 2 days. And I said, OK. And he got it to work. So he proved me wrong, that there actually is enough irradiance to see it. Anyway, so you can just map this time delay. And so here are some images. This is a non-time gated backscattered image. So this is the whole laser beam being backscattered without the time gate. OK? And then this is a time gated image. And you can see it's fairly weak. But what's cool is you scan the time delay, you go from dark into something like this, and it kind of grows, and then it goes dark again. So you actually can carve out planes in backscatter that way, although it's fairly weak. There's 2 problems with this technique. Let me see if I got it listed here. No. 2 problems with this technique. The backscattered light is a little bit weak. And then the other thing is, whenever you backscatter from a transparent drop, or maybe a piece of glass or something like that, you can get glare spots. The light will go in, it will reflect from the back face, it will come forward, and it will be focused. And so you get this focused, intense piece of light coming back. And the spot that you see doesn't really represent the size of the drop, because you know, when it hits as it's coming through, it hits the backside. That's like a mirror that's going to, the retro reflects some of the light. That'll focus it like a mirror will, right? And then this face is going to focus it again. And so whatever you pick up with the camera, it's questionable about what you picked up. Is that doesn't really represent the size of the drop. So there are several problems with this technique that we have to work through, or we won't be able to use it. But it does actually carve out planes in the center of a turbid medium. So we just demonstrated that, and we're still trying to figure out what to do about it. You can still see some things. We actually, that liquid jet I showed you with the acceleration images, we looked at that also in backscatter, and you can still see some things despite the glare spots. So there may be a way to make this useful. We have to see if we can think of a way to do that. Okay, I want to talk about SLIPI now. SLIPI stands for Structured Laser Illumination Planar Imaging. So this is now a planar imaging technique. And you remember, I said when we send a plane through here, you're going to get all this multiple scattering and it'll corrupt everything. This is a way to try to get rid of that corruption. Actually, LaVision sells this, but I don't think anybody's bought it, which has Edward depressed. SLIPI works well for OD around 6, okay? It complements ballistic imaging, which is useless for OD less than 6. Why does it only work? Well, I'll tell you later. I have to explain it first. So the serious problem with sprays is this multiple scattering problem. So if we have a plane of light going through a spray, these photons come out, and as I showed you over here, they come out in all sorts of wonky directions depending on how many times they were scattered and exactly how they were scattered. So multiple scattering corrupts the image. Here's a planar image from inside a hollow cone spray. So it's like this picture here. It's cone shaped, right? It's supposed to be empty in the center. So a laser sheet came through this way, and you notice how optically dense this spray is. The laser sheet was scattered so strongly that this side looks weaker than that side. It's not because the spray is weaker on this side, it's because so much light was lost on this side. But multiple scattering is causing this light in the center. So what's happened is, exactly as I showed here, even though this is a hollow cone spray, so there's no drops in the center here, but drops along the edge have scattered and they have filled in here. And so this thing is supposed to be hollow in the center, and it's not, and it's all because of multiple scattering. So the trick to structured laser illumination is to make it striped. And so the irradiance has a sort of a sinusoidal looking shape to it, okay? So you put a signature on the laser beam. Light that comes out that doesn't have that signature was obviously multiply scattered. Light that is not multiply scattered still has that signature. That's the point. So it's a sequence of horizontal bars. Problem is there are empty spaces between those bars, right? So you basically use 3 of these sheets. This is the weakness of SLIPI. You actually need 3 laser sheets, okay? And they have a spatial phase relative to each other. If you have these 3 and you add them up, they will, if you add them together, they will fill in the empty spots. So they are sinusoids in the vertical direction, 3 different pulses separated by spatial phases that big. So the most common approach would be to take average images for these 3 different phases, and then you manipulate those 3 average images. But if you want good time resolution, you need to actually have 3 laser pulses and a camera that can pick up 3 different imaging systems, basically, or a camera that can capture 3 different systems. You can do that with 2 interline transfer cameras. So if we call these 3 images I0, and then that one with that phase shift and that one with that phase shift, and the final process image is IS, okay, you find the RMS this way. That's all it is, just the RMS image, and that gives you the SLIPI image. You can get a conventional planar image like you would get if you just had a normal plane going through, if you just average those 3 images together. So here's the corrupted spray, and that actually was a planar image constructed of the 3 SLIPI images. We just averaged them and produced that picture. And then here is the slippy picture if you manipulate it with that other formula. So basically what it's doing is rejecting everything that does not have the spatial signature. And this is why it can only see an optical depth of 6. Every digital camera that you can imagine has somewhere inside it an electron well depth. The image photons are turned into photoelectrons, and those are stored somewhere in a well that's like a tiny, tiny capacitor. It can only store so many photoelectrons. So when you fill it up with noise photons that are multiply scattered, you still need to be able to record the ones that are modulated, right? Well, if you overfill it with noise, you won't record what's modulated. And that's why it's limited to an optical depth around 6. But you can see we got rid of the garbage in the center. It's the laser beam was still attenuated coming across the spray, though. This is not a really seriously dense spray, but it's a nice demonstration, right? You can see what Slippy's doing. This one also has glare spots. Not as bad as our backscattering technique, but it also has glare spots. So if you wanted to zoom in on this and try to do droplet sizing, it would not be reliable. But it gives you an overall image of the structure of the spray. So here's what it typically looks like. You kind of blow it up into a sheet. So there's a negative spherical lens, a positive lens. They go through an aperture to contain the size of it. Then they go through this Raunchy grating. You can do this several different ways, but a Raunchy grating is just stripes of reflective material with transmissive material in between. So it's like a top hat. It passes a top hat. Then they use a cylindrical lens to spread that out. And the point is, you see this frequency cutter here? That top hat is actually described by, well, you can think of it as a Fourier sine series. Any top hat could be described by a Fourier series, right? So what you want to do is eliminate all but the first component of the Fourier series. And we don't have time to talk about it, but lenses take Fourier transforms. If you put a collimated beam into a lens and you go to the focal point, what you'll see at the focal point is not the image. What you'll see is the spatial frequency spectrum of the image. So what they do is they carve out that part of the spectrum that is a clean sinusoid and then just dump the rest of it. So you can use, they do this because Raunchy gratings can survive intense laser pulses much better than a fancy sinusoidal transmission grating. Those are very expensive and they get burned easily. So you can get a nice clean sinusoid doing that. Then you make it into a sheet and you pass that through the spray. There are a lot of tricks. You need to be able to align these three things in space so that they add up correctly. They do that by going into a camera and doing Fourier transforms and looking at the spatial frequency spectra and aligning things that way. So it takes all this stuff is built into this product that LaVision sells. But can it be done with 2 pulses instead? Everybody keeps asking that. Can you do it with 2 pulses? Because then you could use a PIV laser, right? Well, the trouble is, with the 2 pulses, you don't actually fill in the information that you need. So this guy Elias Christensen from Lund realized that you could make very, very small stripes and do it with 2 pulses. And then you look at the Fourier transform of the image, and you do some spatial frequency, some, what would you call it? Some filtering. You filter out certain spatial frequencies, those high frequencies that are sort of causing still stripes in your image, and then you get a nice looking slippy image. But if you think about it, what's that really doing? It's passing an averaging filter across. So you're doing some spatial averaging to get rid of these stripes that are there because you did 2 images instead of 3. But you can do that.
How to generate that 3 pulse bursts of different patterns, just use 1 grating?
What they do when they have a pulse burst, you mean to take a single image? Instead of averaging, you want to take a fast image?
In your slide, you mentioned that you need a fast camera and
Yeah.
with different pattern, right? And
Right.
we can got the image.
Yeah.
How to generate that 3 pulse with different
You just get, well, what you do is you get 3 different YAG lasers. But YAG lasers are not
with 3 gratings, right?
in 3 different gratings.
Oh, yeah. That's kind of expensive.
Well, YAG lasers aren't so expensive, but yeah, they're 3 YAG lasers is more expensive than 1, that's for sure. But the way to use an interline transfer camera, you don't, these guys, when they did it fast, they used this extremely expensive camera that was designed for looking at nuclear events, nuclear explosions or whatever. You don't need that. What you can do is, remember that an interline transfer camera can take 2 images within a microsecond of each other. So if you bring the image, if the image is coming in this way, so your slippy is over here somewhere, you can use a beam splitter and go into one double image camera, and then you go into another double image camera this way, and then you fiddle with the timing of the shuttering and so forth. You have to be let's see. We did this with ballistic imaging. Yeah, we captured 3 ballistic images that way, so you can do that. That's kind of a cheap. You have to have a fast shutter in front of that camera, and so there are. Now I'm talking about companies again, but there's this. There are cameras like the Princeton Instruments Pimax, which is that has an interline transfer architecture. It does double images. It has an intensifier on it, which means the spatial resolution is not as good as it would be without, but it has an extremely fast photocathode on the front of it. That photocathode switches in 500 picoseconds. So what you don't want is 3 images to land on your camera. You just want 2 to land on your camera. But with a really fast photocathode like that, you can do it. So you don't need, you need to get 2 Princeton Pimaxes. They're about $60,000 each, something like that. Yeah, so Slippy is not a cheap technique. Other questions?
Just one. How do you align the 3 lasers along the same optical axis?
You have to be very careful about using apertures and things like that. Oh, sorry, how do you align those 3 sheets along the optical axis? You have to be very careful about, you start out by using apertures, right? And then you put things in the flow that'll mark their location, and you look at the camera and see, is it in focus, out of focus, that kind of thing. And then vertically, are you also talking about how you get those matched?
Well, I'm thinking about how one of my lab mates, he does PIV, and he says the worst part about it is always getting the 2 lasers to overlap in space, and then he uses the same cylindrical lenses and whatnot.
Yeah. Well, but yeah, when you do the 3, you mean independently? It takes a lot of care. So you have to go through apertures. You can actually map out the location of the laser beam by passing things through it, right? Have you ever seen that? You can measure the Gaussian waste of a laser beam by passing a razor blade through it. You can do those things and map the locations of the center of the beam, if you have to be really, really careful. Some of these techniques take a lot of time to get set up carefully. In our lab, we use lots and lots of apertures. You should never skimp on apertures. You should buy as many apertures as you can, because when you come back the next day, things will have wandered a little bit, and then you have to put the beam back where it came from. Lots of apertures. Other questions? And like I said, oh, sorry, go ahead.
I think there's a group in Wisconsin that does ballistic imaging with X-rays. What's your opinion of that technique?
There's a group where?
Might be wrong, but I think it was Wisconsin.
There's a group somewhere that does ballistic imaging with X-rays. I'm not familiar with that at all. I know about the groups who do X-ray imaging, and I know about the groups who do ballistic imaging. There are several different techniques for doing X-ray imaging in sprays. One of them is called radiography, and well, let's talk about that real quickly. Radiography is Beer's law absorption. And so you have to be able to absorb the X-rays. X-rays go through things, right? So how do you absorb the X-rays? Typically, they have to either go to softer X-rays or they dope it with something that will absorb. And a lot of people who do sprays don't like the doping. So let's say here's the spray, right? So for radiography, what they do is, and for those of you who've never worked with X-ray, I have worked with X-rays at synchrotrons, but if you've never worked with an X-ray, you can't use any of the things you're used to using in optics. You can't, to focus something, you can't just stick a lens in there. That stuff doesn't work. So they actually use a mirror system. You can reflect an X-ray, so they use a curved mirror system to like focus the beam down, and then it comes out, and then they go into a detector, and they measure the absorption, the level of absorption, and you can calibrate that, and that gives you an absolute determination of the mass in the spray. That works. They do fluorescence as well, which that really does require doping it with something. And so they do radiography at the same time they're doing fluorescence to the side. Okay, they can pick up fluorescence to the side, and then they walk the spray back and forth like that, and they can map that out as well. They do that kind of thing. Now, you might also be thinking about this technique called phase contrast imaging. Is that what you're talking about? Okay, phase contrast imaging is just like shadowgram imaging. To do phase contrast imaging, they use fairly hard X-rays. And typically, okay, if this is the spray, they'll have a fairly large beam go through, and then they'll come through. And it's like a shadowgram. They just come straight through. And then they go into a thing called a scintillator, which is a crystal that will be excited by the X-ray radiation, and it will emit, almost like fluorescence, in the green. So you can use a high-speed camera to get the picture. So they do that as well. And the reason I'm quite familiar with this technique, because I got in big arguments with them, and I did an analysis of the technique and showed that it doesn't work. And the reason is this: the sales, what's supposed to be the really strong attribute of the X-ray techniques is that the X-ray beams don't scatter, right? They just go straight through. And so everybody was always complaining about sprays where their light just kept scattering. And so folks decided, well, X-rays don't scatter, so we'll just go through. But you see, for ballistic imaging, the fact that the photons scatter is actually a good thing. Because if they scattered, that means they are marked as corrupted photons, and you have to find a way to get rid of them. The trouble with phase contrast imaging is that nothing ever goes away. So, and when you go through a drop with to get a phase contrast image, when you see a drop, you just get this kind of shadow of a circle like that, okay? Now, when you go through a spray, which is a whole lot of drops, nothing ever goes away. So you get the signature of one of those things right here, and this is a dense spray. There's a lot of these things, right? You get over here, the signatures of all those things end up all together in the image. And you can't separate them because they didn't go away. So what you get is an image, but it's an image of all these signatures all like pile on top of each other. And if there's something in the center, if there's a liquid core in the center, you can't see it anymore because these things have just done a whole lot of this. So so I modeled that with an electromagnetics code that propagated an X-ray beam through a collection of droplets and showed that that's what happens when you send an X-ray beam through a collection of droplets. You get a lot of this and nothing else. But some of the phase contrast images they've shown are for a jet that has no drops. Then you see a jet that actually makes sense. It looks like what you'd expect in a fluid mechanical sense, except that you can do the same thing with Schlieren imaging or shadowgraphy or something like that. You don't need millions of dollars of budget for a beamline to do that. You can do that in your own lab without a beamline. So there's really no reason to take what's in effect a shadowgram of a spray using X-rays. You don't really need to do that. So those are the techniques I know about that are X-ray based. I also analyzed radiography using the same electromagnetics code, and I showed that actually is a really good technique. So I felt bad about stomping on that technique, so I did a whole analysis of that, explaining why that's a good technique, and it is. That's a good technique.
So I think they also do neutron imaging on X-ray, so how does it compare to...
Say that again?
I think they also do neutron imaging.
Neutron imaging. Yeah, the question is neutron imaging, how does that fit in? And the truth is that neutron imaging is especially useful for looking inside the injector, right? The problems with some of these techniques is you get so little signal coming through the injector that things are... They also do phase contrast imaging through an injector, and I don't have a problem with that because you don't get so much of this corruption, right? The problem in both cases is that so little signal comes through that you can't do high-speed imaging, and that's a problem because these things like the bubble behavior inside an injector is transient, but they're getting better. So we'll see what happens. In the end, that may work. Are there questions? Yeah, X-rays are very interesting. In fact, I sound like I'm a person who doesn't like X-rays. I just think X-rays should be used appropriately for the problems that you can't solve with a simple white light and a camera. I mean, if you can do it with a white light and a camera, there's no reason to fire up a synchrotron. But X-rays can do some things that you can't do any other way. So this is Slippy of a diesel spray, and actually here you can see the stripes. They didn't completely go away. But that's Slippy of a diesel spray. Let's see, did I? Nope, I didn't do it. That's too bad. So the spray went up in this direction, and the beam went across that way. And you can see that it's being attenuated because diesel sprays have an optical depth more than 6, and the beam's gone away, and you can't see what's going on anymore over there where it got really bad. But what's interesting about this is, have you ever heard of a technique called planar laser drop sizing? There was a lot of hope for this technique. It's an interesting technique. The idea is that scattering from a surface is proportional to the surface area, or in other words, diameter squared. Fluorescence from a drop is proportional to the volume, or diameter cubed. So if you take the ratio of a fluorescence picture to a scattering picture, it turns out the ratio should be directly proportional to the solder mean diameter of the drops in the spray, and that's what people typically want to measure, the solder mean diameter. So there was real excitement about that technique, but it had several problems. One of them was that when you get down to smaller drops, it doesn't really scale as diameter squared. The scattering doesn't. So you basically have to, if you start to measure smaller drops, then you have to correct the signal for the fact that it's not really diameter squared. That's okay, you can do that. Then the other issue is you have to be very careful about how much dye you put in the liquid, because you can get very strange non-volumetric signals from drops, because when a planar beam comes through a drop, it will be distorted by the interface, because this is really a ball lens, right? The beam's not going to just go straight through without being affected by the index difference, right? So this ball lens will start to focus light, and it'll cause non-uniform behaviors. So you have to be a little bit careful about how much dye you put in. And then the other issue with planar laser drop sizing was multiple scattering. It just totally corrupted the signal. So these guys actually managed to show that you can use Slippy to do planar laser drop sizing. It has to be calibrated by phase Doppler anemometry. So you have to do phase Doppler at one location. Then you take these images, you do the corrections, and you can actually take an image of the solder mean diameter if you are careful about it. So that's a really great technique. I guess I didn't have that here in this talk. So our next topic is going to be tomorrow, and we'll talk about concepts in molecular and atomic physics, which is starting to get at spectroscopy and absorption and those kinds of things. Are there any questions before we go? Okay. See you tomorrow.